wrote a couple of books. Probably the most popular one was Your Code as a Crime Scene. Um, Personally, it's not the book I read. The book I read is, and I should have it here, Software Design X-Rays. And I read that 3 years ago, and that was a blast. It's one of my favorite books um, because not only he has cool techniques that I learned from and I could use at work, but also it has a different approach to legacy systems. Really, really interesting stuff. Um, he will tell you more about that because his talk is also brain shaking and have you adopt different vision on legacy systems, no matter how big they are. And I really think you can learn a lot of stuff from Adam. So I'm really glad that he is here today to talk with us. Uh, I need to mention also he's a founder of a tool named CodeScene. So he's gonna probably show you how it works because it's all related from his work with legacy systems. I've tested it. It's really, really good. If you have to use a tool to help you work with legacy systems, CodeScene is a really amazing piece of work. So without further ado, Adam, welcome, and the stage is yours.
Thank you very much for the wonderful introduction. And hello, everyone. And welcome to this session on prioritizing technical debt as if time and money mattered. So this is a very broad topic. So I want us to dive right in and start by having a look at the kind of forces that we need to balance when building large-scale software systems. And I do think that these forces and challenges, they are very well captured in something called Leemann's laws of software evolution. And there are several laws of software evolution. So today I want to focus on just two of them, the two I think are the most important. And so let me share them with you and see if they resonate with your experience. So the first law of software evolution is a law called the law of continuing change. And this law claims that the system has to continuously adapt and evolve, or it will become progressively less useful. Is this something that you recognize? Yeah, you probably do, right? The law of continuing change is the very reason why we keep adding new stuff, why we keep adding new features to existing code bases. Because we need to respond to user needs, right? We might have to respond to a change in the market, or we might even have to respond to our competitors. So successful software is never done. What I want you to note now is that there is some kind of tension, some kind of conflict with the second law of software evolution. And that's the law of increasing complexity. And this law claims that when a system evolves, its complexity will increase unless we actively try to reduce it. So do you see the tension here? On one hand, we have to continuously evolve and adapt our code, but when we do that, its complexity will increase, which in turn makes it harder and harder to respond to change. And unless we stay on top of it, we can easily end up in a really vicious circle. And what happens in that case is that we, as a development organization, we tend to note symptoms rather than the real root causes. So let me explain what I mean here. Because this is really challenging, because the symptoms of increasing complexity, they will look different depending on who we are, what our role is. So let's see that you're a product owner or a tech leader or an architect. What you will notice is typically an impact on your product roadmap. You will experience that the lead times for implementing a new feature for doing those continuous changes will increase. It simply takes longer and longer. So, what used to take 2 days suddenly takes 2 months. And as a consequence of the increasing lead times, we tend to get a very unpredictable delivery. It simply becomes harder and harder to guess how long something will take. However, what our end users will see is something different. They tend to experience an impact on the external quality of our code. They tend to see this. They tend to see bugs. And the real root causes of increasing complexity, things like technical debt, are largely hidden, opaque, and obscured. And the reason I say this is because software simply lacks physics. There's no way we can take a piece of software, we can pick it up, we can turn it around, we can inspect it for flaws and complexity and technical depth. There's no way of doing that. So how can we bring visibility to things like technical depth? Well, one possible approach is to start to measure it. And this is something I have seen attempted a number of times. And the way that this is typically done is by, taking some kind of static code analysis tool, something that can kind of scan our source code, and we throw it at the code base, and we kind of look at, all right, what kind of code quality issues can we detect in the source code? The first time I saw this attempted was I think it's almost 6 years ago now. I went to one of my clients in England, and they were working on a code base that was 15 years old. And they had used a static analysis tool in order to try to quantify the amount of technical depth. And the way these tools work is typically to scan the source code and then they identify something that violates a given rule. So for example, you have too many conditionals in a function, something like that, right? So the tool says that, all right, refactoring this code is going to take you roughly 2 hours. So now we have 2 hours of technical depth. Tool continues its scan and it sees that, oh, here's a public method without a comment. It takes 5 minutes to add one. So you sum it up. Now we have 2 hours and 5 minutes of technical depth. You continue like that. And this organization had done this study prior to my arrival. And what they found when doing this kind of technical depth measurement on a 15-year-old code base was that they had accumulated 4,000 years of technical depth. 4,000 years of technical depth. Just to put that into perspective for you, 4,000 years ago, that was here. That's the start of recorded history through the invention of writing. So when I tell this story, I always get curious, what kind of programming language did they use? Right? Probably a Fortran, maybe a Lisp, who knows? But on a serious note, I do understand that 4,000 years of technical depth on a 15-year-old code base, well, of course, a lot of that depth, it kind of grew in parallel by having hundreds of developers working on that code base. So the thing is, it could actually be an accurate estimate. I mean, who knows? But it's definitely depressing. And more specifically, it's not really actionable. Because given 4,000 years of technical depth, I mean, where do you start if you want to pay it down? Is all that depth equally important? We just cannot tell. And this is where it starts to become really, really dangerous to quantify technical depth. And again, this is something I've seen when working with different organizations, that what tends to happen when you try to estimate technical depth from source code is that you end up with a very long list of potential flaws. And at some time, the business is going to have some pressure to reduce the amount of technical depth. So what will happen in this case is very often that the organization puts a quantitative goal on the known issues. So you often hear people say things like, all right, we have 7,000 major issues here detected in our source code. We're going to invest a sprint, or we're going to invest 2 months into whatever, right? Into taking those 7,000 issues and bringing them down to just 5,000. And every time I hear this, I always advise against it. Because to me, going from 7,000 issues down to 5,000, it's a little bit like choosing to jump from the 5th instead of the 7th floor. So most likely none of them are a good idea. And the reason I say this is because we really need to consider what kind of behavior do we reinforce by putting a quantitative goal on technical depth. Because what's going to happen with a quantitative goal is that we, as a development organization, are going to make sure that we meet that goal. So what we're going to do is that we're going to pick tasks and start to solve them. We're going to pick the tasks that we're most familiar with, things that might be in a comfort zone, or things that look rather easy, because we're being measured on a quantitative number. And the reason I say this is because what's always lacking in a purely quantitative goal is the most important thing. And that is the business impact. So if we want to truly understand and address technical depth, we need to look at it from a business perspective. And I'm going to get to that in a few minutes. Before that, I just want to sum up what we have covered so far. First of all, I want to show you that quantifying technical debt might be an interesting exercise. It's often a very depressing exercise, but it's definitely not actionable. More specifically, I want to point out that technical debt just cannot be prioritized from code alone. There's no way of doing that. What we can see in the code might be the remediation costs in case we want to act on the paying down technical debt, but we cannot really see technical debt in the code. Because technical debt is not about the time it takes you to fix the code. Technical debt is the additional overhead of working with potential flaws. That said, it's still an important topic because as a business, you're always going to have this trade-off between improving existing code versus adding new features. Remember the law of continuing change. So we do need to prioritize. How can we do that? Well, those of you who might have attended one of my previous talks or maybe even read one of my books, you know that I'm a big fan of version control data. So yes, we all have our odd hobbies, and version control data happens to be mine. And the reason I like version control data is because I find it so fascinating that as developers, we have used version control for decades. And most often, we have used version control as an overly complicated backup system, occasionally as a collaboration tool. But in doing so, we have built up this absolutely wonderful data source. It's a data source over how we, as developers, have interacted with the system we're building. And we can tap into version control data to get a time dimension into our code, a time dimension that kind of helps us reason about things like how our work shifts over time in different parts of the code. And this is the basis for actually prioritizing technical debt. Let's try to make this specific by having a look at the real world code base. So my first case study for you here is from a code base that some of you might actually have lying around on your desk or maybe even keep in your pocket as I speak. I'm talking about this. I'm talking about Android. More specifically, I'm talking about part of Android known as the Platform Framework Base. And the Platform Framework Base, it's a pretty large code base, so roughly 3 million lines of code, most of it written in Java. And it's been written by thousands of developers. So this is truly a collaborative effort. Now, what you see on the screen here is something I call a hotspot analysis. And I'm going to walk you through that analysis so that you know what you see. First of all, if you look at that picture, you see that there are some large circles, right, with labels on them, the ones that blink on screen right now. Each one of those circles represents a top-level folder in the Android repository. So if this was your code base, you would recognize those labels as the names of important subsystems or high-level components. It's also an interactive visualization, so I can click on it and I can zoom in to any level of detail that I'm interested in. And once I get to the lowest level of detail, as you see here, you see that each file with source code is visualized as a circle. And you see that the circles, they have different size. That's because the size is used to express something called code complexity. So it's like a rough estimate on how hard is this code for a human to understand. And I'm going to show you in just a minute what I use for code complexity. Basically, there are many different options you can choose from. And the simplest one, the absolutely simplest one you could use is just to count the number of lines of code. And there are two reasons why I say this. First of all, number of lines of code, it's an absolutely horrible metric, right? But the thing is that many other metrics are just as bad. And this is actually supported by some real research where you compare things like lines of code to more elaborate complexity metrics. You see that they rarely add any further predictive value. And lines of code is a very simple metric to calculate. The other reason I say that the code complexity dimension isn't the most important one is because complexity has this property that complexity is only a problem when and if we need to deal with it. So if we have some code over here, we haven't touched it in 5 years, well, it might not be ideal but it's most likely not an urgent issue, right? So a much more important question than complexity is figure out how relevant is it? Which parts of the code actually have an impact on our development productivity? And this is data that we can pull out of our version control system. We can calculate the change frequency of each piece of code. We can look at how often do we do a commit in each part of the code, and we can aggregate that. And we can use color to represent that. So what you see here on screen in that visualization is simply a combination of these two dimensions. And the result is what I call hotspots. And hotspots are simply complicated code that we have to work with often. I'm going to get back to the hotspot soon. But before I do that, I want to make a little detour into code complexity and code quality in general. Because I analyze code for a living. I work with code analysis tools, and I go to different organizations and I help them prioritize their technical debt and act upon it. And as such, I'm always looking for things that can kind of save time for me. So if I can pick up a hotspot and I can do a quick assessment of the code quality and the potential flaws, that would save a lot of time for me. That said, I do try to avoid the word code quality. I'm simply not a big fan of that term because it kind of suggests an absolute, whereas the reality is much, much more complicated. And that's something that's well captured in the following research. So let me read out the quote for you here. So this is a research paper that had a lot of influence on how I view code quality. And what this paper says is basically that software complexity is so multifaceted that we're doomed if we look for a single number to capture a multifaceted concept like code quality. Instead, what I did was I took a lot of inspiration from a second paragraph here that claims that the most promising approach is to identify specific attributes of complexity and then measure those separately. So this is something I've been working on a lot over the past years, and I call it code health. Basically, how healthy is our code? It's like the opposite of technical debt, right? And what I did was that I looked at a lot of research and I tried to identify the parts, the design flaws that have the largest impact on our ability to understand and modify code. And just to give you an idea on what I typically include in when reasoning about code is things like low cohesion. So you pick up one of these hotspots and you see that it has tons of different responsibilities. It's doing many different things. This would typically be a code smell that I would like to address, because doing many different things, not only does it put you at risk for unexpected feature interactions, code like that also tends to become very hard to refactor, because with many different responsibilities, you tend to attract many different contributors. Then there are different complexity patterns. I talked a little bit about cyclomatic complexity not being a particularly good metric, lines of code, but there are some code complexity patterns that do have a predictive value. One example is deeply nested logic. So you have if statements inside other if statements, inside other if statements, and so on. There's some pretty good research that shows that those kind of coding constructs are responsible for roughly 20% of all programming mistakes. So it kind of pays off to detect them and refactor that kind of code. Now, these are the things I typically look for when I find a hotspot. Another thing I look for is what actually happens over time. Remember, I said that version control data gives us a time dimension. Because maybe this piece of code is a hotspot because the organization already knows that this is a problem, so they're spending time trying to refactor the code. Maybe that's why there's so much development activity here. To answer that question, I use a different technique that I call complexity trends. Here's what I do. I simply go to the version control history and I pull out each historic revision of the hotspot I find, and then I measure the code complexity, the amount of nesting depth over time in each revision. And the red line that you see here shows the amount of nesting depth. And the blue line, as a reference, shows the number of lines of code over time. And what we can tell just by having a quick look at this graph is that the number of lines of code, it's a hotspot that definitely seems to grow just in pure size. But we also see that the complexity tends to grow quite steeply. So what this means, given our context of complicated code that we have to work with often, we see that when we work with this hotspot, it becomes worse and worse and worse. So this is a typical example of that vicious circle that we need to break. Now, the question is, of course, if you want to pay down that technical debt, who would like to have that task? The hotspot I've been investigating now is called Activity Manager Service in Android. And looking at the data, we see that this is a huge class, 20,000 lines of code. And to make it worse, there have been 74 developers just over the past 3 months. So who would like to refactor this code? Most likely no one, and that's good, because we should never ever take on refactorings at that scale. Because what's going to happen is that we're going to branch out, we're going to work on that branch for months, and we will never be able to merge it back, because in the meantime, all those other 73 developers have made changes to code. So we need to break it down into smaller, actionable chunks of work. And for that purpose, I'm using a technique that I call X-ray. This is one of the reasons why my book was labeled Software and X-rays, by the way, of course. So here's how it works. When I find a hotspot, what I do is I take the code and I parse it into separate functions. And then I look at the Git log to see where do each commit hit over time. And I sum it up, and I get hotspots on a function level. And this is what I use to prioritize a starting point for my refactorings. Let's make it specific by looking at an X-ray from Activity Manager Service. So the number one hotspot in Activity Manager Service is a function called, or method called handle message. And we see from the data from the first column, the change frequency column, that this method has been worked on 98 times just over the past year. So like twice a week, some developers impacted by the excess complexity of that method. And we can get a rough estimate on the complexity of how hard that code is for human to understand in a last column called cyclomatic complexity. So cyclomatic complexity is basically a way of counting the number of branches, right? The number of if statements and so on, and loops throughout that function. And the reason I present it as part of an X-ray is because cyclomatic complexity is good for one thing. It's good for making an estimate on how many unit tests do I need to cover just this function. So what this number tells me is that I need at least 106 unit tests to cover handle message. That tells something about complexity, doesn't it? The column in the middle shows us that handle message is a method with 500 lines of code. 500 lines is a lot for a method, isn't it? It is for sure. But, and here's the good news, 500 lines of code is much less than 20,000 lines of code, which was size of total hotspot. And it's definitely less than 3 million lines of code, which was size of total code base. So more importantly, we're now at the level where we can act upon this data and do a focused refactoring based on how we, as an organization, work with the code. So with the theory behind hotspots covered, I would like to take a step back and explain to you why hotspots work so well for selecting refactoring candidates. So let's have a look at some data. So what you see here is data from 3 radically different code bases. The graphs all show the same kind of data. On the x-axis, you have each file in the system, and those files are sorted according to the change frequency. That is, how many commits do you do to that particular file. And the number of commits is what you see on the y-axis. As you can see from the selection of code bases here, this is code written in different programming languages, right? Developed by different organizations, different developers, targeting different domains, different lifetime spans. Everything is different, right? And yet, they all show exactly the same pattern. They show a power law distribution. And this is something I've found in every single code base that I've ever analyzed. This seems to be the way code evolves. This is good for us because what it means is that most of our code is going to be here in a long tail. That means it's code that's rarely, if ever, touched. So that's the part of the code where we can actually live with some excess complexity. That's the part of the code where we can safely live with technical debt. The problem is when we start to take on technical debt in the hotspots. because due to the high amount of development activity, the change frequency, the cost on that technical debt, the interest on it will skyrocket. So using hotspots, we can identify the head of the curve and know where do we need to focus our efforts the most. But there's more to it. In my latest book, I had this chapter that I called Your Best Bug Fix is Time. And what I did in that chapter was basically that I looked at some research done on what happens to software as it gets older. And there is this really fascinating finding that software that hasn't been modified for a year roughly has 1/3 fewer defects than software that has been worked on recently. So what that basically means is that the older a piece of software is in terms of last modification date, the more likely that that software is correct. And this is interesting because if we consider why does software grow old? Why does software stabilize? There might be different reasons. One relatively common reason that I see every now and then is that it's simply dead code. It tends to be very stable code. It's code that's not even used, right? It's just laying around. And I have to tell you that dead code, that's my favorite, because you can simply delete it and get rid of it. And less code is always better. But then there's a second category of code that grows stable. And that tends to be code that's, I mean, it might be overly complicated. There might be a simpler way of doing it, but that code has been debugged into functionality. It's been battle tested. It's proven in use. It just works wonderfully. And having code of that quality might also be nice. So what I like about hotspots is that they give us a very easy way of kind of separating the stable parts that are likely to be correct from the more volatile parts. And this is something I've been using a lot when working with different testers, right? Because if you do things like exploratory testing, using hotspots to direct your testing efforts is a valuable activity. Now, the last thing I want to talk about before I leave time for questions is the link to legacy code. Because technical debt is frequently misused to describe legacy code, but the two are not the same. They are related, but they are not the same. So what is legacy code? Well, there are several definitions of it, of course, but legacy code to me is code that's typically it lacks in quality somehow, right? And it's code that we didn't write ourselves. And I would say it's the second aspect here that's most important. That's what makes it legacy code to me. And I got reminded of this a couple of years ago. So what happened here was that I did a workshop for a company. And this company, they had two different code bases. So we spent the day analyzing hotspots and reasoning about possible remedies and refactorings in that context. And the thing was that, there were some problematic hotspots, but actually most of the code looked pretty good. So both code bases were definitely under control. I was very confident in both those code bases and the team as well. But then towards the end of the day, someone told me that, we have been looking at these two code bases, but we actually have a third code base as well. So I said, that's really interesting. Shall we look at that one too? And they said, yeah, we can do that, but we don't really have to do a hotspot analysis of it because we know that this third code base is a mess. So I said, okay, now it gets interesting. We have to look at it. So we did. And it turns out we picked up the hotspots, we measured things like code health, and we compared them. And it turned out that objectively speaking, there was virtually no difference between the two first products and the third code base. From a quality perspective, from a code quality perspective, they looked equally good. So how come that the team considered codebase number 3 to be a mess? Well, it turned out that what actually happened was that the two first code bases were written by the current team. The third code base was developed by a different team in a different part of the organization that had since been disbanded, and the team had simply inherited that code. So it wasn't that the code was more complicated or in worse shape, it was just unfamiliarity with the code and its domain. And this got me thinking, if factors like system mastery and how well we know a piece of code impacts how we perceive it, how quickly can we turn a code base into legacy code? What do we need to do? And to study this, we're going to use a different piece of version control data, because version control data is also social data. Our version control system knows which developer that wrote which piece of code and when they did it. So this is something we can use to reason about things like system mastery and potential knowledge loss in a code base. And I want to show you how it's done using a different open source application. I want to study this on a code base called ASP.NET MVC Core. It's a dynamic web framework from Microsoft, written in C# mostly. And we see a visualization here. It's the same visualization style as we use for hotspots, only now the colors carry a different meaning. Blue, in this case, simply means that this is code written by active contributors. So this is code written by the current team. Then we have different shades of gray. And these different shades of gray that you see on different modules, different circles, they simply represent code written by former contributors. So in terms of system mastery, this is code where we have a knowledge gap. This is code where we might not be familiar with the details. And what we can do using version control data is that we can simply simulate what's the impact in case the developer is pulled to a different project or leaves the company or something like that. We can simply simulate what's the effect of that. And I did this on ASP.NET MVC Core. I identify one of the persons that's employed at Microsoft, working full-time on this code base, and I thought, what's going to happen if this person leaves? You know, if you look at the numbers at the bottom, you see there are like 180 contributors in total. So clearly one person cannot make a big difference, right? Let's look at the data that you would see to the right. If just one person leaves and it's the wrong person, then the red areas of that visualization to the right shows the impact. It simply shows you which modules we will lose the majority of the detailed knowledge of, because the code is written by the person that leaves. Should you be worried if this is a real scenario? I would definitely be worried. So what I would do is I would use this data to kind of mitigate potential offboarding risks. So what I would do is that I will look for an overlap between hotspots, because I know if something is a hotspot now, it's very likely we will continue to work on it, and a high code complexity, because then I know it's more challenging to onboard someone else. And third, if we lose the majority of the knowledge of that piece of code, then I know that I have a real offboarding risk. And what I would do now is that I would simply pair together with the developer leaving. I would pair together either me or one of my colleagues that's going to stay around, and we would refactor those hotspots together to mitigate an upcoming risk. So the reason I showed you this is that I really, really want to point out that there's so much more to code complexity and to legacy code than just the code itself. In particular, I found that social factors influence how we perceive a code base. In particular, we tend to overestimate the complexity of unfamiliar code. And on the other hand, we might easily underestimate the complexity of code that we know well. And getting objective data on it really, really helps in decision making. Now, I hope I've inspired you to try this out on your own code bases. So let's have a little bit of a look at the tools that I use to do this analysis. First of all, you have to remember that this is a pretty new field. When I started to work with these kind of analysis, like maybe 10 years ago, there weren't any tools available to do the kind of analysis I wanted to do. So I kind of started to write my own tools. And the first tool suite that I wrote, it's almost 10 years old now, is called CodeMath. I'm still maintaining it. It's been stable for a long time. And CodeMath is a command line tool. It's completely free, available on my GitHub page. It's open source. And it's capable of doing the hotspot analysis. And you can even do some of these knowledge analysis using CodeMath. If you want to dig deeper and want to get serious about technical depth and reasoning about legacy code, I would highly recommend that you take a look at CodeSyn, which is what I work on right now and been working on for the past 5 years. So CodeSyn is the evolution of these IDs. And it's also completely automated. So you basically just point it to your code and you can start to interact and explore your code. It's also completely free for open source. So if you work in that space, please consider to support it. Finally, I think it's worth mentioning that I'm so fascinated with Git because you can get really, really far with just a Git client. And I think my favorite example is what you see here on screen. That did you know that using git log with the -l flag, you can actually specify a function name inside of a specific file and have Git trace the evolution of that function? And this is something that's, like a simple X-ray right from your command line. So there are a bunch of options here in the tooling space. And to wrap this up, I just want to clarify that all the techniques I've shown you today, I don't intend them to replace anything. Rather, these techniques are here to complement your existing expertise and your experience. Because software development at scale and legacy code in particular are challenging. And I'm convinced that we as developers, we need all the support we can get. And I really hope that this session has inspired you to investigate the field of behavioral code analysis in much more depth. And I would also like to leave you with a number of references in case you want to read more on this. So I cover hotspots and knowledge loss analysis and a lot of other stuff in my latest book, Software Design X-Rays. I have a number of interactive analysis that you can play around with at Codesyn.io. So I have prepared a number of analyses of well-known open source systems. So that might also be a good starting point if you want to explore this. I blog regularly on technical depth, software analysis, and software evolution in general at Codesyn.com, and occasionally at my private blog, adamthornhill.com. Now, before I leave time for questions, I just want to take this opportunity and say thanks a lot for attending my talk. Thanks for listening to me, and may the code be with you. Thank you.
Thank you very much, Adam. That was very interesting. So, yeah, we talk about a lot of things: hotspots, X-rays, complexity trends, knowledge loss, and that's a glimpse of everything you can get from Git. Git version control in general, metadata. Git is one of the most popular. So, yeah, if that's your first time hearing about these concepts, you will get a ton from all of the sources Adam presented here. The video will be available later, so do the slides, so don't you worry, we will show that with you. Okay, so we're taking some time for the questions to kick in. Thank you, Adam. Okay, I can see we have questions coming up. All right. So, Adam, how do you handle the authors for when people do pair or mob programming, for example?
Oh, that's a really lovely question. It's of course important to split the blame and credit for everything right in the code base, because I think that if you're doing pair programming, what you typically need to do then is that you need to kind of track that information somewhere. And the typical way of doing that is to have it in the commit message body. So you might have something like GitHub, for example, can insert co-authored by. And what you can then do, if you use a tool like Codesyn, is you can tell Codesyn that, hey, we're doing pair programming or mob programming. And Codesyn will simply take all those code changes and know that this was done by 3 people and kind of split the credit for that, which gives you an accurate way of measuring knowledge loss. So I hope that answers the question.
Yeah. Adi also said, I had the people in the comment. I think it depends on the tool you use to do your commits, but some tools today make it easy to do so. But the old way to do that, have a look. You can put who are working on this in the commit. Again, the commits hold the time information, what is changed, and information about the authors. So it's not because you are pairing or merging that you cannot capture this information. You just need to do it explicitly. All right. Next question is, so static analysis will work for syntactic depth, but what about semantic depth? I think, do you get the question? I think it's about also the syntax versus what it means.
Yeah,
Um, how do you
yeah,
feel about that?
yeah. So I think that static analysis. From my perspective, I'm actually a big fan of static analysis. I use it myself in my day work, but I find that static analysis is useful for me as a developer. So very low level feedback loop to catch possible bugs early, to catch specific omissions. Static analysis was never designed or intended to handle technical debt, right? It's simply not what it's supposed to do. So using it in that area, I think is a mistake. Um, that said, um, semantic depth, so that's more like if you implement the wrong thing or you're having the wrong solution. I don't really think there's any tooling that can help you. Static analysis definitely can, and behavior code analysis cannot really either, right? But what it can do is that what I like with behavior code analysis is that it gives you such a good overview of what does the code base actually looks like. It kind of brings a little bit of those missing physics to software, right? So to me, behavior code analysis is not really about analysis. It's more a communication tool. It's something I use to communicate and make sure that the whole organization has a shared view of what our code base looks like, where the strong parts are, where the weak parts are. And I think building that shared understanding, it's fundamental to all kind of good decision making. So I would strongly encourage you to use it as a communication tool rather than an analysis tool.
Yeah, yeah, I agree. I think it doesn't give you the answer, but it gives you a lot of hints and where to look at, and then you need to use this information to investigate, talk to people, and determine like the reason why, and then maybe you will find the root cause is we're building the wrong thing or something like that. Also, as you said, communicating with non-technical people, these graphs are super useful. When you show the hotspots and you have these big red dots, it's really easy to communicate the value to people who are not into the technical nitty-gritty details of the code base. So yeah, I use CodeSeam in particular for my open source projects also. I use it for fun to analyze some, like the Docker engine, for example. And it's really great what you can learn, even if you are not familiar with the code.
Yeah, that's actually an interesting use case for behavior code analysis. I actually used it myself. Like 10 years ago in my previous life, I used to be a software consultant, right? Meaning I often got to new companies and had to learn a lot of things in a short time. And I
Yeah,
found that, behavior code analysis really let me get that big picture very early on. So I think it's a kind of an underestimated use case for behavior code analysis.
I agree. Okay, we have a couple more questions. Let's take a few more minutes and then we go to break. This one is probably short. What version control system does Kotlin support?
So CodeSyn only supports Git out of the box. If you have something else like Subversion or old TFS or Perforce, what you can do is you can set up an automated conversion to a local read-only Git repository, and then you can point codes into that. So this is something that a bunch of our users do as well. So there are options.
You can work around. Nice. Okay. While paying off technical debt, do you attempt to understand the code base? And if so, how do you go about it?
If I attempt to understand the code base,
Yeah. While you're paying off the technical debt.
yeah,
I
yeah,
think we mentioned, yeah, I think we mentioned
yeah. I
that
think
already.
that's yeah. Yeah, I could elaborate on it, but we can also see, are there any other questions, or should I go ahead with it?
Uh, there is no details. Okay, I think we're gonna skip this one because we don't have much time left. But Raghunath, we can discuss this in the chat if you want later. Okay, the last one. What do you think of architecture or depend? Oh, wait, I lost the question. Okay, what do you think of architecture dependency checks as part of the hotspot analysis?
Ah, that's wonderful. So I have a different talk where we actually show you a behavioral code analysis technique that I call change coupling. And change coupling is very much about architectural dependencies. And it's about logical dependencies, like, one team makes a modification here, now another team over here in a different component or a service, they have to make a predictable change. So I'm a very, very big fan of staying on top of that. I think it's really, really important because hotspots helps you with the isolated part. It helps you with the building blocks. But there can be a lot of complexity in the connections between those building blocks. And the hotspot analysis cannot help you there, but the change coupling analysis can. So yeah, I'm a big fan of that. I think it's really important. And it's information that tends to be really, really hard to keep in one's head. So this is where I think I would highly recommend that you check out the change coupling and behavioral code analysis to support you with that.
Yeah. And also it helps you, if that's the power of version control. You will find coupling that you didn't knew was here, especially between files that don't have the same extension. For example, if you have your backend and your front end, and yeah, you will find some insights. So yeah, I personally encourage you to have a look at CodeSeed. You have use cases of famous code bases, some you may be familiar with. So have a look, and you will see there are much more than what Adam presented here. Okay, if you have questions, don't hesitate to reach out to Adam, to us. Again, video will be available, so does the slides. Don't you worry. We're gonna take a 10 minutes break. I want to thank you, Adam, for being here today, for doing this. Thank you very much. And
Thanks.
Thank you. Well, let's take a break. Thank you, everyone.
Thanks.